Welcome everyone. So yes, it appears I was finishing my class last minute and somehow the K is missing from MegaPlonk. So it's MegaPlonk. But welcome. Thank you for having me here. And so, what am I doing? What am I talking about? Good question. I'm the CEO of Aztec. We are a privacy-preserving L2 core Ethereum enabling end-to-end encrypted blockchain transactions. And MegaPlonk is the cryptographic proving system which underlines everything that we're building, powers everything we're building. And so I'm going to talk a little bit about how it works. It feels thematic for this conference. So there's been an enormous amount of diversification and differentiation of proving systems over the last 5 years. So 5 years ago, I co-authored Plonk, which was one of the first, the first practical universal SNARK that didn't need time trusted setups. There's been a lot of iterations, innovations, and things have changed a lot. The requirements that the various ZK teams building the space have are all very different based off of their use cases and value propositions of their network. And we found at Aztec that our needs are rather unique because of our focus on privacy and privacy-preserving computation. And so when setting out to develop a proving system to power our network, these are basically the desires that I came up with. So I want to efficiently prove a bunch of functions. So these functions are going to represent functions within smart contracts. I then want to take the output of those functions and evaluate what I call a state transition function. So this is basically, I've got some database of stuff, and these functions are modifying this stuff. And there are rules around how these things can be, how this data can be modified. I need to be a legitimate user. I need to have permissions to call certain contracts. I need to be creating valid state updates, etc., etc. I also want to be able to efficiently pass data between all my function instances. So if I have call data and return data, I want to pass lots and lots of information between these functions. And then I want to compose the proofs of all these functions into something which is constant size. And I want this all to be done on the client in a web browser with potato hardware, because we're building a transaction network that supports smart contracts. And so the default way users will be interacting with the network is probably through some gap in a web browser. So if you're controlling secrets, it'll need to be proved within a web browser. And this places a dramatic limitation that is not present for transparent L2s. We have very limited memory that we can consume. And also the size of the proof we're sending to the transaction network has to be very small, because this is going to a peer-to-peer gossip network, because we're a decentralized protocol. And the bandwidth of those is rather limited. So how the hell do we do this? So these are the four, I would say, pillars of a ZK-SNARK today. The idea is that these are modular components, abstractions that you can build, you can lay on top of each other, instead of having to create some monolithic protocol. You have some way of defining your circuit authentication. So you have some way of converting your the imperative program that you want to prove into polynomial algebra. Because in ZK we're very good at proving statements involving polynomial algebra and not very good at proving statements involving anything else. You then construct something called a polynomial interactive oracle proof, which is basically you have a proof, you have a statement about a very large number of polynomials that are all very, very high degree. So they've got millions of times, billions of times of them. And you want to prove some equations of these polynomials that equal 0. And the whole point of the polynomial interactive oracle proof is to convert this relationship over these very high degree polynomials that contain all of information into a statement over something much smaller. So a bunch of individual field elements or points. You then connect the polynomial interactive oracle proof to a polynomial commitment scheme, which is a way of representing an enormous amount of information encoded within these polynomials as singular points of data, either through some kind of Merkleized hash tree or a elliptic curve commitment. And then on top of this, that's basically how you get to a SNARK. But then on top of that, we have this concept that's come out since 2020 of a folding scheme, where it's basically a way of doing recursion, verifying proofs within proofs within proofs, where one can effectively combine multiple circuits, proof statements about circuits, into some kind of weird random linear combination of statements. I'm going to get into folding schemes in a bit. They're rather complicated. They're very useful and very, very, very powerful. So I'm going to talk a little bit about honk first. How does one make an end-to-end ZK-SNARK? So first of all, because the cryptography is very much tailored to the applications and the needs, what is it that we're trying to do with Aztec? Well, we have smart contracts that are privacy preserving. What does that mean? It means that each contract is composed of functions, and each function is a SNARK circuit. And the idea here is that we want to be able to compose contracts. So I can call a contract, and that contract can call other contracts, that can call other contracts, etc. And that all has to be represented within a single transaction. And so a single user transaction is basically a large sequence of proofs of function called SNARKs that need to be composed together and verified in a single we call the kernel circuit, borrow the nomenclature from ZK, where the idea is that the kernel circuit is encoding a portion of a blockchain node. It's verifying that the functions that you're calling are following the rules of your blockchain network. So these functions exist within the smart contracts that are being deployed correctly, you're calling them correctly, and that you're processing all of the inputs and outputs from that contract correctly. So how do we do this? So we have honk, which is our basic ZK-SNARK, but then on top of that, we've layered this incrementally verifiable computation scheme to enable recursion, to enable this concept of a kernel circuit. And this, in turn, requires 3 independent cryptography protocols to implement. We have this folding scheme, Proto-Galaxy, that was iterated from Proto-Star from 2020. We have something we call MegaPlonk, which is basically a way of speeding up these folding schemes and making them fast, efficient to evaluate. And then we have this thing we call the data bus, which is basically a way of transferring lots of information between different SNARK circuits in your recursive instance. But the reason this is important is because the naive way of doing this is through public inputs in SNARK. So if you want information from within your SNARK circuit to be propagated outside, you use public inputs. These are not free. When you're inside if you're doing things recursively or folding, basically every public input requires a hash. This adds up quickly if you have 1,000 public inputs. So we need a faster way. We need something which is what we call constant time. We need a way of transferring information between different circuits where the cost to transfer that information does not scale with the amount of data you're transferring. That's what the data bus does. And so these are some performance targets that we have for honk, for our kind of MVP. We want to make sure that reasonable Aztec transactions can be composed within a gigabyte of RAM, that recursion can be proved in 20 milliseconds, and that the proof size is less than 16 kilobytes, because we have this limitation around what we can send to our gossip network. We'll see if we hit them by the end of the year. So what the hell is honk? So honk is basically derived from hyperplonk, which is plonk with some text. So the original plonk paper, the way that it performed its polynomial interactive oracle proof was you have some polynomial algebra that you want to equal 0, modulo a vanishing polynomial. The idea is you have basically you're committing to vectors of information, and you want to apply some mathematical formula to each vector that represents arithmetic gates, such that you have a gate equation which is 0 for each row. The way we did it originally with plonk was, well, let's encode these vectors as univariate polynomials, and then if you apply that arithmetic equation over the polynomials, instead of it equaling 0, because you have those across terms, the result will equal 0 modulo something called the vanishing polynomial, which is the I've got 20 minutes, so I'm not going to explain all that, but feel free to talk to me afterwards if you'd like to know more. The problem with that technique is that it requires these things called fast Fourier transforms, which are rather expensive to perform, they consume a lot of memory, they're rather annoying. Subject protocols are an older technique from the 1990s that has been adapted to work with plonk. So previously there were some issues with getting subjects to work with plonk. Basically the idea here is that instead of having this weird vanishing polynomial, you have this expression that you want to evaluate at each row of your circuit, and you check the sum of the expressions as 0. Now, this isn't strictly useful, because if I have a bunch of arithmetic gates that have to equal 0, I don't care if the sum of the expressions equals 0, I need them all independently to equal 0. But you can solve this by adding a randomized polynomial into your expression. This isn't even readable. So this is the subject protocol. This is dates back to the 1990s. Basically, the main difference between the sum-check protocol and the original stuff that Plonk did is the representation of your data. Previously, we were encoding vectors as univariate polynomials. Now we're encoding them as multi-dimensional, multilinear polynomials. So that adds significant complexity, but it does make the proving speeds much faster. That complexity is that we lacked until recently an effective way of committing, efficient way of committing it to multilinear polynomials. So the idea is that I want to be able to give a verifier an elliptic curve point that represents a very high degree polynomial with millions of terms. And then the verifier gives me some random challenge. I give them a challenge response, and in doing so, I can provide claims to what these polynomials evaluate to at random points and prove it succinctly. Easy to do with univariate polynomials. There was a kind of the textbook scheme came out in 2013. It's called KZG. Not so easy for multilinear polynomials unless you want to do 20 to 25 bilinear pairings, which are very painful and expensive. So zero-morph is one of the protocols that solves this. It was researched in-house by two of our researchers, Patrick and Tori. And effectively what it does is it shows that there's a linear isomorphism between any univariate polynomial and any multilinear polynomial. That you can basically perform these one-to-one mappings. And so what happens is in zero-morph is you commit to a univariate polynomial. You commit to your multilinear polynomials as if they were univariate polynomials. And then you verify the correctness of this isomorphic transformation. Long story short, it's pretty efficient. It's pretty cheap. It solves the problem that we had, which means that we can make honk multilinear. So, Foley schemes. Hang on, am I on the right slide? Yeah, okay. So let me go back 15 slides. Sorry, there's something that's out of sequence here. Oh, stop now. Can I not go back? It won't let me go back. Or will it? Slowly. Okay. Right, so we're going to skip all these themes for now because we have other slides for that. So, when it comes to honk, how do we visualize our circuits? We visualize them through this concept of an execution trace. The idea is that instead of thinking about a circuit in terms of gates and wires coming out of gates, which isn't that useful when actually it's a useful high-level abstraction, but if you actually wanted to think about how to construct circuits, it's not that helpful. What we think about instead is basically a table of cells where each row represents a constraint and the number of rows represents the number of constraints. And the number of columns is basically the number of polynomials you have that represent your circuit. So the idea here is that we have our execution trace is made up of witnesses and selectors. The idea is the selectors define the circuit. They define what the constraints are, and the witnesses are the numeric values that the proof is providing to satisfy the constraints. And so you can use them to construct basic arithmetic relations, but you can also have this thing. We have this concept of custom gates, where the polynomial relation you're checking can be anything you want. It doesn't just have to be checking multiplications and additions. It could be checking a Poseidon permutation. It could be checking elliptic curve group operations, whatever you need. And so with honk, we've defined a specific configuration of gates because the way that we want honk to be used with an Aztec is you program your smart contract with Noir, and Noir compiles down into circuits. Those circuits get proved and verified within the Aztec protocol architecture. And so we want to make sure that one verification algorithm can basically verify every single honk smart contract, which means making some specific choices about the kind of gates that are available to the developer. So yeah, Plonkish proof systems can have hundreds of custom gate equations. We have about 20, 30. And they can be composed together using this thing called a polynomial identity language. Basically, it's an abstraction layer where you can program polynomial relations as if they were just basic mathematical relations. You don't have to worry about the fact that they're polynomials. This is not not got time for. Okay, so for example, this is the list of gadgets we have in honk. So on the left is basically an abstraction of the trace. We have wires, 4 wires. We have 2 things we call input-output data that are related to the data bus. I'll go through them in a bit. And lookup tables. And the idea is you can do arithmetic gates, you can do efficient range checks, you can do lookups, we have a memory abstraction where you can look up, you can represent memory read-writes in 3 constraints. We have basic lookups for things like bitwise operations, elliptic curve operations. We can do group operations and decided permutations. That's basically the toolbox. This is obviously abstracted away in Noir, but if you want to get down to the brass tacks and actually develop with honk directly, these are what you've got available to you. I'm not going to go through the permutation, we don't have time. Blah, blah, blah. All the ROM and RAM, the memory abstractions, it's all rather efficient, but no time. So, honk is the bare bones protocol, cryptographic proving system we use, but we layer on a lot of other protocols on top of it to actually build what we call Aztec, like the cryptography behind Aztec, which is what we call MegaPlonk. And one of them is this incrementally verifiable computation scheme. Can you read that? Probably not. I can try and describe it. So we need recursion for Aztec. We need to do it client-side because if every single smart contract function is its own circuit, and you have functions calling functions calling functions, basically you just have a lot of proofs that you somehow need to compose together. We also need recursion to chunk up complicated computations because we have a gigabyte of RAM to play with. So what if your computation requires more memory than that to prove? Well, you split it up with recursion. But recursion is historically very expensive. I spent years working on this problem back in 2019, 2020. So when we launched Aztec Connect in 2021, we had server-side recursion. It cost like 800,000 constraints, which was good enough for constructing roll-up proofs. It's not good enough if you want to do that recursion in a web browser. So this is where folding and incrementally verifiable computation schemes come in. The idea is that we have this kernel circuit K, and what it's going to do is it's going to take a previous kernel circuit and a circuit that represents a function call, and it's going to basically use a folding scheme to combine them into something we call an accumulator, which I can get to in a bit if I don't run out of time. And the idea here is that with each iteration of the kernel circuit, we're constructing a list of outcomes that need to happen to the network, to the S network, basically state updates that need to happen. So encrypted data that needs to be added to our database, encrypted nullifiers that need to be constructed, any events that need to be emitted, and also any public function calls that need to be executed, because those aren't done on the client, they're done by third parties, because if you don't need privacy, you don't want to be doing your proofs client-side. And so what I hope this diagram can communicate is that there are a lot of independent, there's sorts of sequential steps that are required to actually construct a proof of an Aztec transaction. And so, yeah, we need an IVC scheme. It needs to be formally defined. We are writing a paper. It should come out, not even soon, but it'll come out before we launch mainnet. So how does the Proto-Galaxy incrementally verifiable computation scheme work? I'm simplified this down to having Proto-Galaxy can fold a large number of instances, like circuits together. I'm simplifying this to just one, so this is actually more like Proto stuff. The idea is that you start out with this thing called an instance, which is you have a committed instance which contains basically commitments to your polynomials. So you have commitments to your execution trace commitments, you have commitments to your selector polynomials, and you have public inputs which are not, which are just field elements. And then the W stands for the witness, so it's all of the actual information one needs to construct a proof, but most of that will not leak out of the protocol. And you have this thing called an accumulator instance, which is very similar to a regular instance, except it has these two additional terms, E and beta, where beta is basically random challenges that have been generated, and E is an error term. What we're basically doing here is we're taking multiple circuit descriptions with witness assignments. So basically quasi-proofs. We're taking also quasi-proofs, and we're constructing random linear combinations of them to basically make a single consolidated proof. And whenever you do that, you're going to get also like weird error terms and cross terms, because instead of checking a gate relation over one circuit, you're checking a gate relation over a random combination of multiple circuits. And So what happens is basically that original polynomial interactive oracle proof from the first slide or so, instead of checking that you have some algebraic relation which equals 0, it's going to equal this error term instead. And the whole thing about faultless schemes is that you can deterministically compute what the error term should be if the prover is acting honestly. So the idea is, given an input accumulator and a new instance, you can fold them together to create an output accumulator instance. That's folding, and then you have this thing called a decider, which is basically, it's the regular prover. You're proving that given your accumulated instance, your basic honk relation equals this error term instead of 0. So the way it works, do we have time? Do we have enough brain cells? So the whole theme of it is basically this error polynomial g of x, where here we have this function fi. What fi represents is all of the algebra required to verify a gate on the ith row of your circuit. And instead of applying this evaluation function to one witness, we're applying it to a combination of two witness transcripts, so W and W1, that we're representing as a low-degree univariate polynomial. So the idea is that normally, if you didn't have multiple witnesses inside inside fi, if you just had fi of W1, then g of x would equal 0. But because we're combining two transcripts, it's going to equal some low-degree polynomial, about degree 20. And then you evaluate g at a random point, and this basically becomes your error term. And then you apply a similar transformation to your committed transcript to construct a new output accumulator, for instance. You know, like Proto-Galaxy is worth like a 1-hour talk to get through, so hopefully that gave a gist of it, but really it's we need to do a deep dive to go through the details. But I can tell you the costs. So this is the cost using Proto-Galaxy to fold honk. Because Proto-Galaxy can fold like generic protocols. We're using it for honk. So the folding verifier requires 32 elliptic curve scalar multiplications and some other stuff which is completely trivial. And this is painful because these are non-native elliptic curve scalar multiplications. Basically, if I have a SNARK circuit over the BN254 curve and I want to do BN254 operations, then I need to do algebra in a prime field that is not the natural field of my SNARK. And this is extremely expensive. And we need to find a way of getting around this problem. So there's a few that have come up. Cyclefold is one of them, but we came up with something slightly different that we called MegaPlonk. So the idea is you've got two cycle curves, A and B, so if you're making a SNARK over curve A, you can efficiently do stuff on curve B, and vice versa. What we do is within each honk circuit, we add these transcript columns to the execution trace, which contain statements about elliptic curve operation. So instead of evaluating an elliptic curve operation in our circuit, we basically just provide the inputs and the claimed result of the operation and shove them in these transcript columns. It's effectively computation deferral. We're saying we're not going to bother evaluating these operations in the circuit, we're just going to provide the result, assume it's correct, and move on. And at some later point, using this transcript, we're going to prove those statements. So the idea is, as the incrementally verifiable computation scheme iterates, we're going to have all these transcript instances from each circuit that's being folded. And so we have this merge subprotocol, which basically just combines them. So the idea is, for each IVC step, you have an accumulated transcript and an input incoming transcript, and we combine them. This time, though, we don't create random linear combinations, because we want to be able to prove each elliptic curve operation independently. And we can't yet do random combinations yet. I'll explain why in a bit. But the idea is this is basically adds a trivial number of constant group operations to the IVC verifier. What's the point of this all? Well, the point is that if we have a bunch of commitments to the elliptic curve operations over curve A, we can provide a commitment to the same operations over the cycle curve B, and then construct a proof that the information encoded in these two different commitments over two different fields is the same. So the idea here is that for your input transcript, which is over FA, the scalar field of curve A, and your cycle curve transcripts over FB, we want to prove that the same. How do you do that? Well, you construct a SNARK circuit which evaluates a polynomial defined using the coefficients within the original transcript columns, but you use non-native field arithmetic to evaluate this polynomial as if it is using kind of B-scalar field. So this is not particularly cheap to do, but this operation has to be done a very small number of times per elliptic curve operation. So the idea is that we have this formula on the left-hand side, use non-native field arithmetic over a circuit defined over CGA. On the right-hand side, you just use a polynomial commitment scheme because over curve B, and you check that those quantities are the same. Once you've done that, then the last step is quite trivial, which is, well, you now have commitments to your elliptic curve operations, but now they're defined over your circle curve, which means they're efficient to evaluate. What's basically happened is that a very, very large sequence of non-native elliptic curve operations has been transformed into a sequence of native elliptic curve operations, which are very easy to validate. So overall, the costs are going to be, so for honk, if you have 32 scalar moles you need to do to verify each IVC step, that translates to about 40 native scalar moles and 240 non-native field operations, which is about 20 times faster than brute forcing this. And we basically, that's kind of the result that's borne out in our measurements. So to summarize, yeah, it makes recursion super fast, is what we needed. The last component of MegaPlonk is this data bus. So this is a little old. So there have been memory checking techniques that came out a couple of months ago by Zac Williamson, I believe, which probably supersede this. But hey, you know, the performance is roughly similar, and we care far more about just securing our code base and not implementing new stuff if it's not going to get, it was only going to give marginal gains. The idea here is that in our execution trace, we add these columns that we call call data and return data. The idea is that you can pass information between successive steps of your IVC trace. And we use the lookup protocol to basically transfer information from these two columns into the rest of the execution trace. So the idea here is you have these pi symbols represent instances that are falling together. And so when you start, in your first instance, you don't have any call data because it's your first step in the chain. You just have return data, which is propagated into the second instance as call data, and then the second instance is return data becomes the call data instance of the call data column of the third instance. So R1 equals C2, R2 equals C3, and on you go. And this is actually really easy to do because what you do is because if you have one of these quasi-proofs, your call data, return data columns are represented as succinct commitments, elliptic curve commitments. And so all one has to do is propagate, if you are in one of your IVC steps, if you're folding the previous instance, you take the commitment to the return data from that proof, and you just propagate it via public inputs up to the next instance. The idea here is that at instance I+1, you can possess both the commitments to your previous instance as call data and the previous instance +1 return data. And you just check the commitments match. And voila. Basically, it's a very efficient way of propagating information between these various steps of your IVC chain. And it means that we can, for example, in Aztec, we can communicate thousands or 10,000 field elements between instances very efficiently, which is exactly what we need. And the costs are their constant size. It's basically 4 group operations in the following verified. So I have 20 seconds left. So this is end-to-end honk. This is actually wrong. I haven't completed it yet, but if one cares to look, at some point I will finish this. This is basically about a quarter of the formulae for the protocol. But that's it. Thank you very much. I've been Zac. Thank you for listening. Do you have time for questions?
Maybe it's a stupid question, but how do you compare your work, cryptography, to Hyperable?
Yeah, I didn't mention that. So they achieve different ends, is the way I would say it. So with Aztec, every single smart contract function gets compiled down to a bespoke SNARK circuit. This is to maximize efficiency. Basically, we want to directly represent your program via the most optimal constraints. But this means that when you're doing an IVC and you're folding instances together, the actual circuit descriptions could come from a million different smart contracts. And Hypernova is particularly good at folding the same circuit instance over and over again. It's not good if you're folding instances that can come from a set of 1 million. I don't believe it has an efficient way of doing that, and Criticality does. So that's basically the main difference.
But I think Supernova can do that, right?
No, it can't. So there is something in the paper called bucketing, where the idea is if you're folding one of a small set of instances, it works. Because the idea is that you have k buckets for k circuits. And for each IVC step, you fold your new instance into one of the buckets. That doesn't work if you have a million buckets, because then you're not folding anything. You're basically, it means your final verifier has to verify a million different circuits instead of one.